All right, here we go. So chapter 4 is a new unit, okay? And this unit is all about how we apply all of the things we learned about derivatives, okay? Now, I'm not saying that to instill a sense of fear or panic in you, okay? I'm just saying that we are getting a second chance to look over some of the content that we've learned and think about, how does this apply beyond a piece of paper where I turn in something and like, that's the course, okay? And so what I find really exciting about this particular chapter is for those of you who are thinking about going into engineering or any sort of science or even into business, that there are a lot of applications in what we're gonna learn to those fields. And it's a little bit easier to see now why we do all the things we do about slope when we have a context to do things in, okay? And so with that, we are going to start with section 4.1, which is related rates, okay? And so let's start with what we know. So things that I hope we know are the average rate of change versus the instantaneous rate of change, okay? So thinking about that slope between 2 points as the average rate of change and that slope at a single point as the instantaneous rate of change, okay? We're also going to bring back this idea of implicit differentiation. So that thing where we had like the y and the y prime, okay? And then we're also in this section going to bring back the chain rule. So those two pieces, if that's something you felt like didn't quite make sense for you in the last chapter, we're going to get another chance to look at it, but in the context of some actual applications. Okay, so it might actually be that like now with an actual problem that has a meaning and a physical meaning, that it actually makes a little bit more sense for us. Okay. And so the question that we're going to be asking ourselves today is this one right here. Okay. How do quantities change over time? Okay. So the big thing here is that things are changing over time, right? So let's start with the concept here, okay? So let's take a look at this scenario. You have, let's say, a balloon. It's filled with air, all right? Now, I don't know if there are any secret mathematicians out there who like to make balloon animals, you know, where there's like the long balloon and then you could like twist it into like a dog or something like that. I've never been able to do that. I feel like every time I try and do that, I end up with like the balloon pops, you know, or I'm just like so scared that it's going to pop that I don't twist it in the proper way. Ooh, how fancy. We do have some mathematicians out there. I love it. Okay, well, in this case, we're going to think about sort of like the typical balloon, like a round balloon, or I don't know, a sphere. Okay. So in scenario 1, let's in our heads think not about balloon animals, but about just a regular round balloon. Okay. Now this balloon is getting filled with air. And so my question to you is, let's think about how these quantities change with time. Okay. So you've got your balloon, it's filling with air. What is happening to the radius? Tell me about that. Is it increasing? Is it decreasing? Is it staying the same? What's happening?
Increasing because it's getting bigger.
It is increasing, yes, exactly. So we can say that this one is increasing. All right. What about the surface area of the balloon? Or like, you know, the actual physical part of that balloon? Is the surface area going up or is it going down as we fill it with air? It is
Yeah.
yeah, exactly. All right, what about that volume? The amount of air inside that balloon. Increasing, decreasing, staying the same?
Increasing. And what did you mean by like going up and down?
Oh, I just meant that increasing is the same as going up.
Oh, okay.
Decreasing is the same as going down. Yes. Okay. All right, so we agree then, if we have a balloon that's getting filled with air, the radius is getting bigger, the surface area is getting bigger, and the volume is getting bigger, okay? And so what I'd like to do is this, actually. Let's sketch a diagram of the balloon at 2 seconds, and then separately, let's sketch the diagram of the balloon at 5 seconds, all right? So if you can annotate on the screen, go ahead and do that. Pick a corner of the box and draw your balloon, what you think it is at 2 seconds, what you think it might be at 5 seconds. Oh my God, Thea, I love that you put the little like place where you blow the air into there. All right, so Graham has one balloon that popped after 5 seconds. All right. All right, maybe I can throw one of my diagrams in here. So I might say at 2 seconds that my balloon looks something like this. Yeah, but then after 5 seconds, exactly, it might be like larger, right? Oh, look at how happy all these balloons are. I love it. Okay, so we've got the idea here is that the balloon at 5 seconds should be larger than the balloon at 2 seconds, right? And we knew that from thinking about the radius and the surface area and the volume. But before we leave this problem, let's jot down a couple of formulas that might be helpful, okay? So Google is your friend, all right, in case you ever forget these formulas, but let's have a place where we write them down just so that we can refer back to them more easily. Anyone happen to know the formula for the surface area of a sphere or the volume of a sphere? 2 pi r, okay, if you were thinking about just a circle, like a two-dimensional object, maybe. But if I were to put a little bit more detail on here, I might draw sort of like a little fancy belt around this to show that it's sort of three-dimensional, right? And same thing here. This is like three-dimensional.
4 pi r squared?
Yeah, 4 pi r squared. Exactly. That is our surface area formula. So surface area, I know some people just write A. You can totally write A as well. And then I typically draw the little shape that I'm looking for. So surface area of a sphere equals 4 pi r squared. Good, very nice. Whoops. All right, and then volume of a sphere. Anybody able to find that formula? V of a little sphere. Nice, nice, nice. 4/3 pi r cubed. Okay. All right, so let's keep these two formulas in mind, surface area and volume. Let's keep our visual in mind that we can have something that is expanding in size because it's filling with air. And now let's go into a question, okay? So if a balloon is being filled with air at a constant rate of 2 centimeters cubed per second, okay? How fast is the radius changing when r equals 3 centimeters? And then separately, how fast is it changing at r equals 6 centimeters? Okay. And so the way we're going to work through this problem is going to be sort of a typical format that we're going to use for any related rates question, okay? Now, right off the bat, I want us to notice a few things, and that in particular is the units, okay? Units will be your best friend here if you let them be your best friend, okay? The units tell you so much about what is happening, so much more than I think the words around it, actually, okay? So let's think about this rate that they've given us right here, okay? Is that rate telling me how fast the radius is changing? Okay. Got a yes, and a no, and a no. Okay, so let's think about the units now. Let's look at these units. If the radius was changing, what would the units be? Let's actually go back up here and write those out. If the radius were changing, okay, we would say dr, how the radius changes over time. And the units for that rate of change would maybe be like centimeters per second, something like that. Okay, because radius is measured in centimeters and time, maybe we measure it in seconds. Okay, and maybe I should write it as an up and down fraction like this, so we can sort of see how the pieces match a little bit better. That the change in radius is in centimeters, while the change in time is in seconds here. So let's go back to this again. I have 2 centimeters cubed per second. What do we think this is telling us about the radius, the surface area, or the volume? Ah, the volume. Excellent, excellent. Well, look at that. This centimeters cubed, that right there is making us think, volume. Okay. So I can maybe go back up here. For volume, I would write dV. So the change in volume over the change in time. And that might be something like centimeters cubed per second. Okay. Now, while we're here, what might we write for the rate of change of surface area in terms of units or a fraction? Centimeters squared per second. Good. So we might say the change in surface area over the change in time might be centimeters squared per second. Okay. Ooh. All right, so now let's go back to our question for a moment. So we have a balloon that's being filled with air at a constant rate of 2 centimeters cubed per second. So right off the bat, I'm going to say volume equals pi, 4/3 pi r cubed. Now, the reason I'm writing out the volume formula is because this right here actually gives us dV dt. So how the volume is changing with respect to time is 2 centimeters cubed per second. Okay. Now, if I tell you how fast the volume is changing, do you know how fast the radius is changing? Like just from looking at the problem. And when you said yes, what do you think that rate of change of the radius is? Okay. Okay. It is, okay, so 2 centimeters cubed per second tells us about how the volume is changing. But this is not the same as how fast the radius is changing. Okay. Exactly. So because we have dV/dt, it is not the same as dr/dt, meaning that not every part of the balloon changes at the same rate. Okay, some parts change faster, some parts change slower, some parts change differently at any given moment in time. Okay. And actually, if we think back to Graham's picture where he had the small balloon and then his popped after 5 seconds, right? When you're blowing up a balloon, you're inflating a balloon. I remember when I was little, like the hardest part was sort of getting it started at the beginning, right? Trying to get that first puff of air in so that it goes beyond that and then it keeps going, right? But as the balloon grows, what happens as it gets really close to the biggest that balloon can be? Does it get easier or harder to blow air into the balloon? Okay. What about as it gets really close to the popping point? Do we think that it's easier or harder then? Easier. Okay. Scary easier. All right. So, I mean, just from that example, we can tell like it was really hard at the beginning. So the rate at the beginning might be slower than the rate at the end, right? That rate is going to be different. So the way we find this out is all about derivatives. Okay, when we take a derivative, we get that instantaneous rate of change. We know what is happening exactly at that moment. Let's go ahead and use derivatives. We don't even need physics. Let's go ahead and use derivatives to figure out what's happening. Okay, so I'm going to go ahead and take the derivative, but I am going to take the derivative in relation to t. Here's what that looks like. dv dt. Okay, that's the derivative of v. That says this is how the volume is changing over time. Now I'm going to take the derivative of the other side. So I pull all my constants to the front, and then I take a derivative of r cubed. I get 3r squared. But because it's with respect to time, I need to consider the fact that the radius is changing with respect to time. Okay. So just like we knew that when we take a derivative of y, we get y prime. When we take these derivatives with respect to time, we need the bottom to be a dt. Okay. Let me clean this up a little bit. dv dt equals, let's see, this 3 and that 3 reduce. Okay. So not 6, centimeters squared. But 4 pi r squared dr dt. All right, so derivative, I'm going to abbreviate with respect to as WRT with respect to time. Okay. All right, now we have an equation. And this equation down here describes how the volume changes and how the radius changes with respect to time. Like over time, at any given moment, if we plug in numbers, we will get the slope or the rate of change at that moment in time. Okay. So let's plug in some numbers. For t equal, not t, r, for r equals 3, we have, let's see, dv dt we know is 2 equals 4 pi, radius is 3 squared, dr dt. All right. This looks like a very dressed up version of a problem where I have to isolate a variable that I don't know. So we're going to get dr dt all by itself. And we're going to do that by dividing all of this away. So I get dr dt equals 2 over 4 pi times 9. Let's reduce that a little bit. And we'll get 1 over 18 pi. And the units for this are going to be centimeters per second. Okay. Now let's try the same thing at r equals 6. What do I put in to this equation for r equals 6? Six instead of 3, right? And that's going to be the only change. Everything else is going to stay the same. And I'm going to solve for dr dt. I'm going to reduce a little bit. That is how fast the radius changes over time. Okay. So let's kind of look over this one more time. So the number that we're finding, okay, our dr dt, that tells us how the radius changes over time as the volume changes over time. Okay. So Eric, that is exactly right. This 1 over 18 pi is how fast the radius is changing when the radius is 3 and the volume is changing at 2 centimeters cubed per second. Okay. Now, Yithan, why 2? Because dv dt is 2. So if we're plugging numbers into the equation, we're going to fill in a number for dv dt and a number for r. The only thing we won't know is dr dt. All right, let's take a look at the surface area of the balloon. Okay, so this question was about the volume changing, and then we wanted to know how the radius changed. Now, question 2, though, is saying how fast is the surface area of the balloon changing when r equals 3 and r equals 6. Okay. So if this question is asking me for surface area of the balloon, perhaps the first thing I should do is write down the surface area formula for the sphere. And from above, we know that that's 4 pi r squared. Okay. Now, if someone is asking me how fast that surface area is changing, they are asking me for the change in surface area with respect to time. Okay, so if we translate that in our head, when someone says, how fast is the surface area of the balloon changing? They're saying, we would like the derivative of surface area, please. Okay. So let's do that. Let's find our derivative. dSA dt equals, what's the right-hand side of this equation going to become? When I take the derivative of 4 pi r squared with respect to time. So I need a derivative here. 2r, no, that is not correct. Any other guesses? 4 pi times 2r. Okay, so we're going to take the constants, move them to the front. Then the derivative of r squared is 2r. Now this would be not good enough. Okay, and I call it not good enough because we're missing the concept of what we're doing here, which is that everything is changing as compared to time. The way this is right now, this is saying, how's the radius changing as the surface area changes? But we don't know that information. We only know how things change over time. And so this piece right here, without this, we've missed the concept of the problem. Okay. We'll also have nothing to solve for, which is sort of a problem. But just like you really wanted to not forget your y primes when you did implicit differentiation, you really don't want to forget your dr dt's or your dv dt's and having that dt in the bottom. Okay. All right. Now, once we've taken our derivative, we can plug in the numbers and see what we have. So let's go with r equals 3. What does this formula look like? The derivative of the surface area with respect to time equals, I'm going to go ahead and take the 4 times the 2 and make it an 8. So 8 pi times 3. And we can actually grab our dr dt from above. We said that was 1 over 18 pi. And we'll do a little bit of computation here. I think we end up with 1 and 6, and then this is 4 and 3. And so we should end up, oh, the pi's cancel too, my goodness. And we end up with the surface area changes at a rate of 4/3. And the units here will be centimeters squared per second. Okay.
Professor,
Yes.
I have a question. I think you just said this, I missed it. What does having the dr over dt right next to the surface area in the change of surface area over change in time, what does that mean again?
So what we're looking for, we only know how things are changing in time, okay? So it's almost like, imagine you had this balloon and you have a timer, okay? So at 0 seconds before you start, you measure everything, the radius, the surface area, the volume, okay? Then you blow up the balloon and at 1 second you stop and you measure again. What's the radius? What's the surface area? What's the volume? You're going to do that again at 2 seconds, 3 seconds, 4 seconds, et cetera, okay? And so everything that we're doing in terms of collecting data, we only know how these things change over time. But what we don't know is if we change the radius, how does the surface area change? So it's almost like we don't have a direct connection between the radius and the surface area. So we need to go through this new variable of time.
Oh, okay. Thank you. I think I got it now. I think I missed that chunk where you explained it.
No worries. This is a big concept. Okay, so in the chat, so basically it's implicit differentiation. Yes, this is basically implicit differentiation. We were doing other way around, dy over dx. Okay. Yes, and so basically we're saying we need to use chain rule here or implicit because we don't know how they relate directly to each other. We have to think about how they go through another venue, okay? It's almost like, okay, you know what this is like? This is such a silly example, but I don't know if you ever gave a note or you received a note in elementary school where it was like, my friend likes you, my friend thinks you're cute, right? That person who wrote that is not necessarily the person who has feelings for you, but they're using a third party venue to communicate that to you. Okay. Or if you ever play that game telephone where like you say something to someone and then they say it to the next person and keep going down the line, and by the time you get to the end, the message is like totally jumbled. Well, we hope the message is not jumbled here, okay? We hope that the message is really clear, but we just can't go directly there. We have to kind of go around, okay? And Richard, to answer your question, so you see that 4 and the 2, we just multiplied them to make the 8. Yep, that's it. That's it. We just took the 4 and the 2. Let me write that here. We multiplied them to make an 8. That's it. Okay. All right. So if we do the same thing for 6, we can plug in everything. We have 8 pi, but this time we're going to have a 6. What am I going to use for dr dt when the radius is 6? Because I better not use the same value I used before. For radius is 3. Yeah, we're going to use the other rate that we found. Exactly. And when we do a bunch of canceling out this time, this is 9, 2, 3, we end up with the surface area changing at 2/3 centimeters squared per second. So it's a little bit slower. As the balloon gets bigger, it gets closer to that popping point, the surface area is going to change less and less as you expand. Okay. All right, so let's do this. I think this is a good time to take a break. Let's come back at 10:38. But I noticed there's some really good discussion going on in the chat, and I really appreciate the conversations that you're having, both with me and with each other. I think that one thing to keep in mind is it's totally okay to respond to someone else's chat, to contribute your ideas, even if you're wrong. That's okay. I think we're all kind of trying to unpack this together. Okay. All right. So let's do this. We're going to take a look at scenario 2. Ba, ba, ba. All right, so we're going to take a look at scenario 2, and then we're going to skip the next page. We're going to go through a couple examples, then we're going to finish class with that page 3, I believe it is. Okay. All right. So scenario 2 says a ladder is leaning against a wall and begins to slide down the wall. All right. So let's take a moment, and I say let's all annotate what we can. All right. So if you have any answers here, you want to sketch a diagram, go for it. Formulas that you think might be helpful, let's do a brain dump, and let's just kind of go for it. Right. And so there's place on the left for folks who maybe don't feel like drawing. You can answer those questions like, are they increasing or decreasing or staying the same? You can draw an arrow up for increasing. You can draw an arrow down for decreasing. You can say not changing if it's not changing. But in addition to the diagrams, let's see if we can answer these questions, or based on the diagram, what formulas are kind of coming to mind. Okay. So I'll give you folks a few moments to jot that down. Look at these fancy pictures, way better than mine. I think they are pressure washing the house. So if it's really loud on my end, I'm really sorry about that. They're like literally right outside my room right now. I love these diagrams so much. Yes, Christina, that length stays the same. Write that down if you can, or if someone else wants to write that for her. I love that. For the second and third question. Okay, so the distance from the top of the ladder, like if the ladder is like this, there's a distance from that to the ground, that would be vertical. But in the distance from the bottom of the ladder to the wall, like the bottom of the ladder, if we think about the diagram, the bottom of the ladder is like right here, right there. And so that one's going to be horizontal, right? So we've got a vertical component, we have a horizontal component as well. Awesome. I love this. I love this. Okay. So we've got some answers, we've got some diagrams. Let's unpack this. Okay. So length of the ladder, that stays the same. And Christina, that is such an important point. I know, I love Humpty Dumpty there. The length of the ladder staying the same actually makes the question so much easier for us, okay? So we do not want this to be one of those like magical extension ladders where it gets longer as it falls down the wall, okay? The ladder is gonna stay the same length. It's pretty basic ladder. And let's take a look at what folks said for the distance. So yes, as the ladder sliding down the wall, right? Let's see if I can annotate on top of this. The ladder, this distance is decreasing. That's excellent. And this distance is increasing, right? So just by looking at the picture, we were able to unpack that information, okay? And let's see, sketch a diagram of the ladder at 0 seconds and then 2 seconds later. All right, so no matter where our ladder was at, so let's say I had a diagram like this and a ladder like this, all right, by the time we get to 2 seconds later, maybe it looks more like this, right? So think about it as a little animation. That ladder is sliding down the wall. So we get a new picture after 2 seconds, okay? Now, what formulas might be helpful? We've got a squared plus b squared equals c squared. That is in fact a very useful, a very useful formula for what we have here. Trig occasionally, I think not in this particular example, but it can be in other questions sort of like this, okay? All right, so let's kind of start with this. Let's go ahead and take a look at an actual question, and we'll use all of this stuff to help us out, okay? This is always the saddest part for me when I wish we could make this stay. I'm gonna try and cut and paste them in later, but yeah, so sad. Okay, so this is what an actual question might look like, okay? A 10-foot ladder is leaning against a wall. If the top of the ladder slides down the wall at 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? Okay. And so one thing I would encourage you to do for any of these situations is draw a diagram. I know we did that above, but I'm going to go ahead and redraw a diagram. And my diagrams tend to be, I mean, I don't think I'm as artistically talented as some of you folks, but also in the context of trying to answer a specific question, I sort of draw what I need to draw, okay? We could use OneNote or something. Oh yeah, that could be a way. Okay, so we've got a wall, we've got the ground, and we've got a ladder. All right, so I'm just gonna draw the ladder like that. All right, now a lot of things are sort of like things we hope for, in that we hope that the wall and the ground meet at a 90-degree angle. I know that's not always the case, but we sort of assume that to make our lives a little bit easier, okay? And you can label this however you want, but I typically label any horizontal distances as an X value and any vertical distances as a Y value, okay? And if I'm using X and Y, then it sort of follows that the third side is Z, okay? But you could use A, B, and C, it doesn't really matter. How you label that, okay? But each side of your right triangle should have a different label. And then in addition to that, I like to label the diagram with any of the numbers that I'm given, okay? So for example, I know that at the moment in question, the snapshot I'm looking at, we have X equals 5, right? The bottom of the ladder is 5 feet from the wall. I also know that Z is going to be 10 because the ladder is 10 feet long. Now there's one more piece of information that this word problem gave us that we have not addressed yet, which is the top of the ladder slides down the wall at a rate of 2 feet per second. Does that go with the X, the Y, or the Z? It goes with the Y. Now, I'm not going to say Y equals 2 because that doesn't really make sense for our context of figuring that out. But what can I say about 2? Like, what does the 2 equal? I think if we take that y and that t and we put that together, right? As soon as we see that word rate, we want to think derivatives. Okay, exactly. So we're going to say dy because that's what we call that side. If you use h to call that side, you can call it dh. Okay, so dy dt equals 2. Okay, now one question for you. We said that distance is decreasing, right? The y value gets smaller and smaller as we go. How can we accommodate for that getting smaller with our number 2 here? Yes, that negative sign. So I'm going to erase the 2, and in front of it, I'm going to write negative, and then I'm going to write the 2. Okay. Now, your gut instinct was so spot on that if something is getting smaller, we're going to say that rate is negative. But if something's getting bigger, we say that rate is positive. Does that make sense? A smaller rate is negative. Increasing in size will give us a positive rate. Okay. So we've got our label diagram right now, and that is, I think, a really great place to start. Where I like to go next is the formula that I'm going to take the derivative of. So we're going to use, I think it was Moon who wrote a squared plus b squared equals c squared, but I'm going to use x squared plus y squared equals z squared. Okay. Okay. Now for right now, I'm going to say, let's leave them as variables and then we'll take our derivative, but that is exactly where we're going with that. Okay. So start with our formula. We are now going to take derivative with respect to time. So that's going to give us 2x dx dt for the first term. What will that give us for the y squared term? All right, if we take the derivative of the y squared term, 2y dy dt, good. 2y dy dt. And if we take the derivative of the other side, we'll get 2z dz dt. Okay. I tend to, at this point, divide both sides by 2, just because every single term happens to have a 2. You do not need to do that, okay? I tend to do that because I like to work with smaller numbers, right? But again, if you keep the 2 in there the whole time, that's totally fine. All right, so now let's substitute in what we have. So I have x. In place of x, I'm going to put 5. I don't know dx dt, so I'm going to write dx dt. Plus, I don't have a value for y, but I know that dy dt is -2. I know that z is 10. I do not know dz dt yet. Okay. So it kind of looks like, even though we labeled our diagram with everything from the word problem, we still don't have enough information. Okay. Now, of the 3 things that we don't know, like we don't know dx dt, we don't know y, we don't know dz dt, which one of those is the question asking for? Yeah, the question is asking for dx dt. And we would know that because it says, how fast is the bottom moving along the ground? Okay, so that green highlighted part means dx dt. Well, if dx dt is what we're looking for, then we better know y and we better know dz dt. Otherwise, we can't answer the question. Sometimes we have to use the information we have to find some of the other pieces, okay? Now, let's go back a moment to Christina's point that the length of the ladder did not change, right? That was a very important observation that she made, that the length of the ladder does not change. So what is, if z is the length of the ladder, what is dz dt then? Like this is the change in the length of the ladder. What number can we put in there? I see one person typing in 0. How do we feel about that? That dz dt is 0. You like it, you like it. Okay, okay. So I agree. We can say, and I'll label this here, that dz dt equals 0 because the length of the ladder is not changing. Okay, the length of the ladder is not changing. So the only other thing I need to find right now then is y. I go back to this diagram. I've got the x and the z. How do I find the value for y? And maybe it's helpful to strip down that diagram just to be like this, because I think if we look at just that simple diagram without all the other pieces, we might remember, oh, this is just the Pythagorean theorem, right? And so it would be important that we plug numbers into the right places. So 5 squared plus y squared equals 10 squared. And so we'll get y squared equals 100 minus 25 is 75. So y equals quarter to 7. Okay. So we've got this. It could be helpful, I think, in this problem to write this as 3 root 5. Nope, that's not right. 5 root 3. But we don't have to do that necessarily. Great question. So plus or minus, well, if we had a plus, that would mean like how high the ladder is above the ground. If we had minus, that would mean like somehow our ladder fell into the ground and we were measuring it from there, right? So yes, in a regular problem, plus and minus, right? When there's no context at all, plus and minus. Right, exactly. But in the context of this very real situation, we want to consider maybe the positive is the only case that works. Okay, but great question. Okay, so now let's plug in all the things we know. We've got 5 times dx dt plus 5 root 3 times negative 2 equals 10 times 0. All right, so this is going to go to 0. Excellent. And I am going to take this term and move it to the right-hand side of the equation. So 5 dx dt equals 10 root 3, right? Because the 5 times 2 gives us 10. And one step to get dx dt by itself. And we have 2 root 3 feet per second. Okay. Now, let's go back to this conversation about positives and negatives, though. We got a positive answer out. That means that our x distance is growing. It's getting bigger. That makes sense, right? Because even before we looked at this question, We knew that if the ladder is sliding down the wall, the vertical distance is getting smaller, but the horizontal distance is getting bigger. Okay. All right, how do we feel about the ladder problem? Okay. Pythagorean theorem comes back quite a bit in this section. It is one of the more common formulas. All right. But let's skip page 3 for right now. Because again, I want to make sure we get through enough examples. I do think this is because every question sort of has a different flavor. I want to get through as many of those different flavors as possible. Okay. So skip, 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 skip. We'll come back to it. Great. Here we go. All right. So let's take a look at example 4. All right. You and a friend are riding bikes to a restaurant because you want to be environmentally friendly. So you're going to bike to a restaurant instead of adding to your carbon footprint. All right. But I don't know, maybe you don't have Google Maps or you read it wrong, right? You think that the restaurant is in one direction, particularly you think it is east, and your friend thinks that the restaurant is north. So you leave, but you end up going in different directions. Okay. Now you leave from the same point, all right? You are riding at 16 miles per hour east. You're going pretty fast. And your friend is riding 12 miles per hour north. They're going fast, but not as fast as you because you're better. All right. After you traveled 4 miles, at what rate is the distance between you changing? Okay. So as you kind of read that again, I'm going to start with a diagram here. Okay. I don't know if I've shared this with you before, but I remember one time I was trying to do actually a calculus problem, and my dad was very frustrated that I didn't understand what was going on. So he was like, if you don't understand the problem, just draw a bigger picture. I was like, I don't think the size of the picture matters, but okay. But turns out, I think the bigger you draw the diagram, the more space there's to label things. So maybe it does help. All right. So let's start with the starting point. So let's say our starting point is right here. And let's go with what you are doing first. So you are riding east, which means you are riding this way. Okay. And since this happens to be a horizontal direction, I'm going to call this X, which means that since I'm looking at rates, I might at some point need a dx dt. So I'll put that here too. Okay. Can we fill in either of these values with what we know from the word problem? X equals 4. I love it because you traveled 4 miles. Love it, love it. Okay. Do we know our dx dt? Yes, 16, exactly. 16, because check this out. Even though we say mph and we mean miles per hour, it's really the same thing as saying miles over hour, right? That's what mph means. And so again, those units are kind of very, very useful, okay? All right, so this is you. Let's see what's happening with your friend. Your friend is riding north. Your friend is off this way. I don't know what they were thinking. I don't even know where the restaurant is in this problem, but clearly you did not agree on where you were going, right? Now, one thing we do know for sure, though, that north and east meet at a 90-degree angle. And since this is vertical, I might label this side as y. And since I'm looking at rates, I might label a dy dt as well, okay? I know, imagine they went west. That would have been so terrible. Okay, so let's see what we can fill in. Is there anything we can fill in just from the numbers in the word problem without extra work? Y equals 4. Now, how did you get that? I see some for dy dt. Okay, so 12 for the dy dt. Okay, how did you get y equals 4?
I
Or
got it from the word problem.
was that?
I got it from the word problem. It says
Mm.
after you traveled 4 miles. It's
Ah,
actually refer to you.
yes. So you
Whoops.
literally means you going east. Okay. It does not tell us how far your friend traveled, right? Because remember, you're a better cycler than them. You went faster. So they probably didn't go as far as you went, right? Okay. Richard, you got 3 for the y value. How did you get that? Because that is correct, but it takes some extra work to get there. So we travel 4 miles, right? Your friend sucks at pedaling. Maybe they don't have a fancy bike like you have. I don't know. Okay, so 16 miles per hour. So you can solve for how long you've been riding for. Okay, so you and your friend did not travel the same distance, but you did ride for the same amount of time. Okay, so it's like you biked 4 miles and then you stopped, you texted your friend, you were like, where are you going? Right? So at that moment, you both stopped. And so let's see, 4 miles over 1 times, let's see, 1 hour over 16 miles. Well, that gives you, actually, let's not do it that way. Let's do it this way. So 16 miles per hour, but you went for a total of 4 miles. And so the question is like, how long did you bike for? And it looks like you biked for just 15 minutes. Okay, so a quarter of an hour, or you biked for 15 minutes. Okay. So now you both biked for 15 minutes. So how far did your friend travel? Well, we could do a little arithmetic and figure out that they biked 3 miles. Yes, you could also set it up that way. That is absolutely fine. Okay. All right. Now the distance between you two. Oh, we have a hypotenuse. The distance between the two of you is the z value, okay? So z, and we might need to know dz dt. Okay. Exactly. You might need to reevaluate this friendship afterwards, but I don't know. That's okay. You could, or you could just be really forgiving. Maybe they read their map wrong. It's fine. Okay. So let's write an equation to start with, okay? Now, out of this picture, the equation that comes to mind is, as Moon pointed out earlier, x squared plus y squared equals z squared. That does not mean that every time you see a triangle, you want to use this formula, but you have a triangle and you have all the sides, then we want to use this, okay? I'm going to take the derivative, 2x dx dt. I'm going to be lazy and get rid of those 2's. And then I'm going to fill in the number. All right. So I filled in the numbers. Turns out we still have two things that we don't know. But which one of those is the one that we want to find in order to answer the question? Ooh, is it Z or dZdt? Like, which one is the question asking for? Yeah, the question is saying the rate that the distance between you is changing. They want you to find dZdt, okay? That means we got to find Z. So let's strip down our triangle. We've got a 3, a 4 for the legs. What do we have for Z? Yeah, we got a 5. Good job, right? We could use Pythagorean theorem, or we could say this triangle comes up enough. I'm going to call it 3, 4, 5. Okay. So now let's see what we get. We get 4 times 16 plus 3 times 12 equals 5 dZdt. So in order to get dZdt by itself, I'm just going to divide by 5. I think this ends up to be 100 over 5 or 20. And what units do we want to put on that? Miles per hour. Very good. Okay. Exactly, Thea. Miles per hour. Okay. So turns out we use the same equation as the ladder. However, we want to keep in mind the reasons we use that. One, it's a triangle and we know the sides. And two, we know specifically it's a right triangle and we know the sides. Okay. All right, let's actually skip to, oh, sorry, Christina, you had a question about why, how come y is 3? Okay, so does it make sense that we knew you were only biking for 15 minutes? Does that part make sense? Okay, now you both biked for 15 minutes. You just went in different directions. So if you're biking 12, if your friend is biking 12 miles per hour, that means in 1 hour they go 12 miles. How far did they go in half an hour? Yes, it's a fourth, right? So in a half an hour, they only go 6 miles. But in a quarter of an hour, that 15 minutes, they only go 3 miles. Okay, cool. All right, let's take a look at example 8, okay? I know that's kind of skipping around. Yeah, so if you're not looking at a 90-degree, like a right triangle, then you would have to use like law of cosines or law of sines, perhaps. Okay. All right. So we're actually going to start to talk about that in example 8. Like, how do we know we're not using x squared plus y squared equals z squared? Okay. So let's take a look at example 8. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's angle of elevation is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay. I forget exactly who it was. It might have been, I can't remember, but someone asked a lot earlier on in the class about like, how do we know if we're in radians or degrees? And I said that most of the time we're working in radians. One way you can tell, especially in a related rates problem, they'll give you the units in the rate of change. Or if they tell you pi over 4, we know we're working in radians. We know we're not working in degrees. Okay. All right, so let's start off with a diagram. All right, so we've got a level field. All right, we've got a liftoff point, and we have a hot air balloon. Well, that's not bad for a Monday morning. I'll take that. We have a hot air balloon that is going straight up. Okay, so it's not going side to side. It's just going straight up from the launch point. Now, there is a rangefinder or something that's measuring the height of this hot air balloon that is 500 feet away. All right, so this distance, it's a horizontal distance, so I'll call it X, but we know specifically that it's 500 feet, okay? Now, is this horizontal distance changing? Let's start to think ahead here. What do we know about dx dt? It is 0, right? Because even though the balloon goes straight up and down, it's not going side to side, which means that the horizontal distance is always 500. Okay, so we can say that dx dt equals 0. All right, now we know some stuff about an angle of elevation. So we want to think that this rangefinder sort of watching this balloon go up in the air, and it has an angle of elevation. And at that particular moment, it is pi over 4. Okay. Do we know anything about d theta dt, or how the angle is changing over time? Do we know anything about? Yeah, great job, David. This is a rate of change. We have a rate of change. So we can say that it's 0.14 radians per minute. Very nice. Now, is this angle getting bigger or is it getting smaller? It is getting bigger. Good. So I'm actually going to, just so we're clear, it's increasing. So I'm going to put a positive sign in front of it, 0.14. You do not have to write the positive sign, but it might be a reminder for your brain that sometimes that rate is positive and sometimes that rate is negative. Okay, and we need to know which one it is. All right, so now I'm wondering, we've done a couple of these examples, not a ton, but I'm wondering if you can tell me this saying how fast is the balloon rising at that moment? In terms of variables, what are they asking for? That is so great. dy dt. They want to know how this part is changing. So we can actually say, well, y, I don't know what it is yet, but dy dt is what I'm looking for. Okay. All right. Now, here's the tricky thing. let's focus on the triangle for a moment, okay? So I've got a triangle. I've got specifically a right triangle. I know the opposite side. I know the adjacent side. What formula might I want to use here? Like, what formulas do we know that relate an opposite side of an angle to an adjacent side of an angle? Tangent, yes. Okay. That thought process right there, that is how we figure out which equation to use. Okay. So I'm going to write my tangent equation. Tangent theta equals opposite over adjacent. I could even write this as tangent theta equals y over x, since I already have those variables. Okay. All right, we've got our equation. We know we're looking at rates of change. Let's go ahead and take our derivative. All right, so derivative of tangent is secant squared theta. Because we're considering this sort of like chain rule, or because we're measuring everything as it changes over time, we need a d theta dt. Equals, what rule will I need for the right-hand side? I want to take a derivative. Yeah, I'm going to need quotient rule. Okay, so let's kind of do this off to the side. I have u equals y, v equals x, but our du and our dv is going to look a little different here. Our derivative of x is going to be dx dt. Our derivative of y is going to be dy dt. Okay. I'm going to go ahead and plug those into the quotient rule. So x times dy. X times dy dt minus y times dx dt all over x squared. All right, let's see what we get. So I'm going to substitute in values. Secant squared of pi over 4. D theta dt is 0.14. Secant squared is the derivative of tangent. Right, so we're taking a derivative on both sides. Yep, exactly. Taking a derivative now. Once we got our formula, we take the derivative so that we can take care of all these rates that we have. Okay. All right. I know x is 500 times dy dt, which I don't know, minus y times 0 all over 500 squared. Okay, so this last line here, all I did was substitute in the values I have. Now we're going to manipulate a few things here. Okay, y times 0 is going to go to 0. So I actually don't need to worry about that term. Additionally, one of these 500s will reduce with the other 500 on the bottom. There's one last thing that we're going to take care of here, and that is, what is another way to write secant? Maybe a nicer way that involves values that we know. 1 over cosine, exactly. So this 1 over cosine notation is going to be way more valuable for us. So we can write this as 1 over cosine of pi over 4 squared times the 0.14 equals, let's see, dy dt all over 500. Okay. All right. Cosine of pi over 4, hopefully a nice value that we know now, which is going to be root 2 over 2. I want to square that. I'm also going to multiply by 500 here, so I already have my dy dt by itself. Okay. I did a couple things at the same time. I multiplied that 500 over, and I gave a value for cosine of pi over 4. Now, one thing I think sometimes we get lost in fractions, but whenever we have a 1 over fraction, that's really asking for the reciprocal. That's all that's asking. So I'm going to go ahead and write this as 2 over root 2 squared times 0.14 times 500. And then I'm going to square both the top and bottom. That will give me, let's see, 4 over 2 times 0.14 times 500. And this is going to give me, let's see, 2 times 500 is 1,000. 1,000 times 0.14 is going to give me 140. So dy dt equals 140 after a lot of computation. What are the units for dy dt though? Right? What are the units for dy dt? And it might help us to consider what is y measuring. Yeah, feet per minute, right? Y is measuring a vertical distance measured in feet, right? And it's not measuring an angle, so we don't want to have radians. But more specifically, our units should match our top and bottom here, meaning the top units should be the y units and the bottom units should be the t units. So we'll get feet per minute as our answer. Okay. So let me sort of zoom in here for a moment. How are we feeling about that particular problem? Okay. In Calc 3, you tend to see more that things like more than, you'll end up with more variables. It's not necessarily that time becomes the z-axis, but you'll just be able to handle even more things changing. So it's not like, you know how our balloon is only going straight up and down? Exactly. Your balloon might go to the left or to the right a little bit. Now you have different things to consider, okay? Yeah. It's super exciting though. Think about all the things you could actually solve. All right. And you kind of like this one better than the others. Good. Okay. Well, let's do this. All right. Let's do example 7. Let's see how much time we have after this. We'll do example 7. I'd like to take some time to figure out that sort of table to summarize what we've covered today. But let's do example 7 and then kind of figure out what we have. Actually, no, Calc 3 is more like it can be 4D, but mostly it's like 3-dimensional. Like you'll see our pictures are mostly kind of flat, or we're only comparing 2 aspects of any picture, not more than 2. That's when you get into the multivariable, you'll work with more dimensions. Yeah. Okay, so example 7. A tank of water in the shape of a cone is leaking water at a constant rate of 2 cubic feet per hour. The base radius of the tank is 5 feet and the height of the tank is 14 feet. At what rate is the depth of water in the tank changing when the depth of water is 6 feet? And so let's start off with a diagram. And weirdly enough, when we talk about tanks that are in the shape of a cone, it's actually that the pointy part is facing down. So looks a lot like an ice cream cone. It's not sort of like the pointy part on the top, okay? So we're saying that the pointy part is on the bottom, so you can imagine the bottom being where things come out of, so where things leak out of, okay? So let's take our diagram, let's label it with the information we're given. So the base radius of the tank is 5, so I'm gonna say that the biggest radius is gonna be 5. Okay. And the height of the entire tank is 14 feet. All right. Now, how much water is actually in the tank? Well, it's not all the way full, but we actually have 6 feet of water in the tank at that given moment. Okay. So I think that's most of the numbers, but there is this 2 cubic feet per hour. If I were to use variables to describe this, well, to describe this 2 cubic feet or feet cubed per hour, how might I assign those variables? Okay, we've got a dV dt. Well, let's see. Volume, yeah, we measure that in feet cubed or cubic feet. And hours, yeah, that's how we measure time. So I think dV dt is a very reasonable guess. Okay. So all we did here, we said, you can think about it like comparing the units. Volume is in cubic feet and time is in hours. Okay. Now I left a space in front of this 2, right? I left a space in front of this 2 on purpose because we are leaking water. Exactly, Thea. The water is leaving the tank. So we want to have a negative in front of there because the actual amount of water in the tank is going down. It's decreasing. We're losing volume because there's a leak. And that kind of makes sense. Okay. All right. Let's set up a few more things. All right, for this one. I know the base radius is 5. I know the height is 14. What is the radius right here? That little pink line, what is the radius at the pink line? Is it 5 feet? No, it's not 5 feet, right? There's no way it's 5 feet. It's going to be smaller. Okay, so it would be important to think about a relationship to establish how much smaller it is. Okay. So let's set up maybe this ratio. The radius is 5. The height is 14. Radius, height. I'm going to cross multiply here. And then I'm going to say R equals 5/14 times H. Okay. My starting formula here is going to be the volume of a cone, which is not a formula we've seen yet today, but is 1/3 pi r squared h. Okay. Now, this is as far as we're going to go in this particular problem. Okay, this is actually one of the questions on the quiz. So I want us to sort of practice connecting the dots a little bit. Okay, I'll make a few suggestions. So here are a few suggestions. If I want to take this derivative, I actually have too many variables because we're not in Calc 3 yet. So it might be valuable to grab some other information that we have and perhaps do a substitution before we take a derivative. Okay. Let me say that one more time. Here's our formula for volume. We know we need to take a derivative. However, because we're not in Calc 3 yet, we might realize we have too many variables. So my suggestion is to grab some of that previous information, make a substitution, and then go about your business of finding the derivative. This is just the formula for volume of a cone. Okay, so the 1/3 is part of the formula. Yeah. All right. I think what we can do is set up number 5 sort of in the same way. We'll get a diagram down, we'll get a formula down for that, and then we'll finish up with that last page that we haven't gotten to in the notes yet. Okay. So example 5. A 6-foot tall person walks away from a 10-foot lamppost at a constant rate of 3 feet per second. What is the rate that the tip of the shadow moves away from the pole when the person is 10 feet away from the pole? Okay. All right, so let's start with our diagram. All right, so we've got a lamppost and we've got the ground, and we know that there is, interesting, a triangle. We've got a person with very long legs who is walking. And if we labeled this information, we might call this side here 10 because the lamp post is 10 feet tall. But we might label this as 6 because we know the person is 6 feet tall. And we might be able to label this distance here as, and let's call this X, as 10 because at that moment, the individual is 10 feet from the lamppost. Okay. Now the question is, what is the rate that the shadow is moving? And so what we're really trying to figure out here that makes this one a little different than the others is we want to find the rate that this whole part is changing. Okay. And so the way we're going to do that is we're going to find the rate of this part. And then we're going to find the rate of this part. And we're going to take those two and we're going to add them together to get the rate of the shadow. Okay. Now, this diagram tends to be really visually confusing for me. I find it a lot easier when I think about it as sort of a big triangle where this is 10, and then a smaller triangle where this is 6. So that's like the person. Okay, so it's almost like this triangle. I just drew it down there. And then separately, the bigger triangle is the one on the left. Now, the thing about these two triangles, they're both right triangles, but they're also similar triangles. Similar meaning the ratio between the sides is the same. Okay. Now, we know that we have this distance down here, which is going to be 10 plus, and let's give this blue distance a letter. Let's call it A. So 10 plus A. And then this down here is just A. Yeah. Okay. So now I know that these are similar triangles. I can set up a ratio. In fact, I can say 6 over 10, which is this is the 6 over the corresponding side, which is 10. All right. And I'm actually going to go back and change one thing. Instead of 10 plus A, I'm going to write this as X plus A, just because I know at this moment X is 10, but what if we wanted to find it for another moment in time? Okay. And so if we set up the other side of the ratio with corresponding values, we'll get A over X plus A. And that is because we have this over this. Okay. Now, it turns out that this is the formula that I'm going to want to take the derivative of. But like, I don't want to use quotient rule. So I'm going to do a little bit of algebra before I take my derivative. In fact, I'm going to go ahead and cross multiply. 6 times x plus a equals 10a. I'm going to get 6x plus 6a equals 10a. 6x equals 4a. Now I want to find a derivative. Okay, I could have found it earlier, but this form is just easier to take a derivative of. So we get 6 times dx dt equals 4 times dA dt. Okay. And let's go back and see. There's one last number we didn't use yet. This constant rate of 3 feet per second. Is that 3 feet per second the dx dt or the dA dt? Like, is that how fast the x distance is moving or how fast the shadow is moving? All right, we've got one guess for a dA dt, 2 guesses, 3 guesses. All right. It is actually, in fact, not dA dt. Okay. If I could animate this guy or this lady, whoever this person is walking away from the lamppost. This distance is growing at 3 feet per second. Okay, so because of that, dx dt is 3, and dA dt is what we don't know yet. Okay. So we do a little bit of manipulation. We get dA dt equals, I think, 9/2 feet per second. That gives us how fast A is changing. And the 3 gave us how fast X is changing. So if we want to find that overall rate, we're going to need to add our dx dt plus our dA dt. And so the 9/2 is part of our answer, but we need to add that to the 3 to get our total rate, which I think ends up being 15/2 feet per second. Okay. So lots of triangles today, lots and lots of triangles, but depending on the information given, sometimes we use Pythagorean theorem, sometimes we use trig, sometimes we use similar triangles. It all kind of depends on the context, okay? So great question here. If we were to look at the angle between the shadow and the ground, so maybe if someone said, hey, that's cool and all, but I really want to know about the angle changing, then we would need to involve some sort of trigonometry as our formula. Okay. So I know this was a lot. It's sort of like fire hose in the face in terms of a lot of different things, right? But I think one thing that I learned from the results of your exams was how important it is for me to be really clear about how we make these decisions, right? So part of it is sometimes you got to do a lot of practice to figure it out, but there are also sort of breadcrumbs that we can put out there for ourselves along the way. Okay, so again, as you're doing problems, I would really encourage you to have those discussions like, how do we know we need this formula? And don't be satisfied unless you understand the reason that someone gives you, right? This is your education. You got to advocate for yourself more than anybody else, all right? So that being said, let's take the last few minutes to kind of do a quick summary here, okay? So related rates means we are looking at how related quantities change with respect to time, right? So this is what I was trying to say earlier. We might not know how the radius change connects to the volume change, but we can compare them to time and then find out that way. Where are my notes? Okay. So when things are changing with respect to each other, it might look something like this. Let's say we have volume equals 4/3 pi r cubed. So this is just the volume formula for the sphere. If I wanted to say, I know how the radius change connects to the volume change, then I could just take a derivative like this, dv dr equals 4/3 pi 3r squared. Okay, so if they're directly connected, I don't need dt. But if they're changing with respect to time, so same starting formula, what's different though is this becomes dv dt equals 4/3 pi 3r squared dr dt. Okay, so the dt is this with respect to time. All right, so I thought it would be useful to see the setup and how they're different from each other so that we can remember when we need to use the dt and when we don't need to use it. Okay. The second thing I'd like to leave you with is this. Since we're introducing a third variable chain rule or implicit, that's our best friend, okay? When I'm comparing how y changes to how x changes, it might look like this. The derivative of x is dx dx, which is 1. And what we learned from the last chapter, when I take a derivative of y, I end up with dy dx, and sometimes we call that y prime. So this was like chapter 3. This is chapter 3. But in chapter 4, occasionally, when we're looking at how things change with time, the bottom here becomes a t. And so this becomes dx dt. And I can write a similar statement for y. This is dy dt. Okay. Neither of these equal 1. So it's really important to keep that in mind. If you're taking a derivative with the x, there better be like some derivative to show that rate of change. Okay. All right. Last thing I want to leave you here with is a list of some common formulas. So we've written out a bunch of them already, but let's just kind of have them in a nice place. Let's start with the circle. Okay, so I know we didn't see circles a lot today, but sometimes we see just a circle. So circumference of a circle is 2 pi r, and area of a circle is pi r squared. Okay, so those are 2 nice formulas to have in your back pocket about circles. Next, let's look at the sphere, which we've already talked about today, but the volume of the sphere is 4/3 pi r cubed, and the surface area of the sphere is 4 pi r squared. Okay. Volume of a cone. I think we just used this one, so 1/3. Whoa. Pi r squared h is a good formula to know. And that actually comes from the volume of a cylinder, which looks exactly like that formula, except no 1/3. Okay. So volume of a cone, volume of a cylinder. What else? What else? Okay. And then our triangle formulas. So we know that a squared plus b squared equals c squared. And then maybe thinking about some similar triangles that we can always set up a ratio, something like this, to be helpful in terms of similar triangles. Okay. You can add to this list as you come across other formulas that we might need to know, but I think we can kind of leave it at that for right now. The biggest trick here is how do you know when to use which formula, okay? And Yithan, exactly, if you took a cone out of a cylinder, then there would be like 2 cones left inside there. So 3 cones fit inside 1 cylinder. The first square, this one? Okay, cool. All right, so that is it for related rates. Yeah, a lot of these formulas do come up from that. We use them again and again. We'll probably be using some more of those on Wednesday when we look at a different kind of application. Yes, I just realized she might not be done, and that was terrible. There you go. You can both see now. Okay, so I will post the notes and the video at the end of class.